So the last time I came to the park, I discussed how cool it would be to be able to do science out here, where instead of taking samples back to the lab or to my home, we make the chemical measures we need out in the field where those samples already exist. Well, today I'm going to be using the TrinamiX Near-Infrared Spectrometer to make those chemical measurements. So the park is an interesting place because there's all sorts of surfaces that we can measure. There's a playground, a baseball field, a tennis court, a walking path, litter, everything here. So even in this shot, you can see that we have a lot of green grass, brown grass, and presumably this would tell us how much water is in the soil surface. We can see right here, we have some litter, and presumably this would give us a different chemical signature than the ground around it.
Welcome back to the channel. I am now back indoors, and after a very exciting outdoor adventure with, as you could see, this small device here is a portable near-infrared spectrometer by TrinamiX, and I will introduce the device and then go a little bit more about the history. But this is a small Game Boy sized portable near-IR device. It has a sapphire lens with 6 tungsten lamps, and the idea is that it measures the absorbance of this NIR light. So there's a lot of sensors and a lot of technology that goes into building devices that can be this small and this robust. I have already probably taken 200 or 300 measurements with this device alone, just to go to get the feel for it. And by and large, it definitely feels pretty robust in the hand. I have several things already planned, from looking at pharmaceuticals to agrochemicals to other things that I think would be a really cool data set to collect and walk you through the design of those experiments and to publish and share with you either through GitHub or other means. So to operate the device, this NIR source, you simply push this button here in the middle, and you have a few LEDs that gives you the indication of whether the instrument is connected or needs to be calibrated and the battery level. Calibration for this device is really straightforward. You have a little plate that pops off. You have this white reflective surface that you then place on the device like this. And so after getting an ambient light reading, you then take your second measurement here, and the device remains calibrated. If you change some of the settings, you have to recalibrate, but generally speaking, this device remains pretty well calibrated even up to a couple hours, even though I think the recommendation is to recalibrate every hour. And after running probably 200 measurements, I still had 97% battery life. So this device is definitely capable of working all day, measuring, taking lots of measurements. And so really cool. And we will push those limits. And I can see that depending on the application, this would make for a device that can sort of go with you out wherever you are, which for a field deployable device is very important. If you look here, I am showing you the specs of the device, 1400 to 2400 nanometers, a pretty solid spectral resolution, especially in this small device range. And you can see some of the other specs here, 6 tungsten halogen lamps. The lifetime is greater than 100,000 scans. And this lamp module can be replaced pretty easily. Just turn this piece and pull it out. The sample interface is a scratch resistant sapphire window. Here the dimensions, like I said, it's about 570 grams, which is just under 1.5 pounds, and has some reasonable dust and waterproofing, which is necessary for outdoor usage. As far as the temperature, which is usually what can separate, a part of what separates indoor instruments from instruments that can deploy in situ, is the operating range, where most indoor instruments, because of the optics, because of the sensors, needs to be in a well-controlled environment. This actually has a fairly wide operating range, 0 degrees Celsius, so freezing up till fairly warm at 40 degrees. When charging the device, should be a little bit cooler because the device can heat up a little bit depending on how much you're charging. And so this, guess I've charged this up a couple times and usually only use about 5 or 10% of the battery. Mostly just to explore the software, get used to it, and then we'll eventually be going out and carrying out some pretty robust studies. But I will show you some of the data that I've collected so far. So when interacting with this device and once it's on, most of the access is done via some sort of software, either on a phone or an iPad. And you can see a glimpse of the software here, where there are some built-in models for looking at byproducts in skin, or you can run your own data studies and store that in a data collections folder. In this case, I will show you a couple of the studies that I'm running and the data I will make public, and has allowed me to understand the merits of this device, how well it works under various circumstances, and also, again, try to get me more comfortable using this sort of sapphire sampling surface, because in practice, you should be placing your sample right up against this sapphire glass. So yeah, that's just part of getting more into the spectroscopy world. So next, let's move to interacting with the data. So to access the data in the cloud, so the data isn't stored on this device. It's actually cached on the phone and then quickly moved to the cloud, where you can access the full data set to help build models or bring it down for data processing, which is typically how I'm going to be interacting with the data and demonstrating that process for you. You can log onto the cloud portal, log in. I will log in with my Google account. And from here, I can see I have my applications, which are, if I have models already built to, in this case, there are pre-built models for looking at skin moisture, at looking at the nutrient parameters for various cereal grains, and some other byproducts. Or you can design your own campaigns in which you can collect the data and see the raw data. And I've got 2 active campaigns. One looking at food products like apples, oranges, bananas. In this case, I was actually juicing and wanted to look at the IR spectra, NIR spectra of the various fruits. So I will use this more as a classification type data set. And then I have my nature data set, in which I have made 228 measurements, 20 samples, and those 20 samples include various flowers, fruits I've seen outside, even some dog feces. But what I will focus on also is this park sample, in which I went across the way to one of the parks in LA and made several measurements just within this particular sample that I'm leaving unlabeled, so that we can now look at clustering and other forms of unsupervised analysis to see what types of data we have. So if we go to the measurements, we can see that each measurement has either a description, if it was applied, a sample identifier, some other unique characteristics that we will see once the data has been downloaded. And we can see all of the spectra through this study. And so to download the data, you can select all the results and then download the data in a number of different file formats: Excel, CSV, a binary file type, and then you could zip the files. In this case, I already have the data downloaded. And once we have a new study that I'm running, I'll walk through this whole process in real time for you. But I want to at least give the overview of the workflow and what we can do with this device. And then, like I said, I will break this down further. So I took a stab at just looking at some of the preliminary data I have in my data set, and I am using Python and VS Code to do that. And so I began with all of these standard Python libraries: Pandas for data processing, Matplotlib and Seaborn for data visualization, as well as Plotly Express. You'll see why soon. And NumPy for some of the signal processing as well. The data is downloaded in and I've moved it to my instrument data folder. You get a timestamp, the name of the campaign, and some of the metadata associated with the run. And I am reading that entire data set in using the first column as the index column, and I'm just sampling the park data for now. And so I'm storing that as DF. When I run that, and then I look at the first 5 rows of data, this looks like a standard data frame where we have our measurement ID and sample ID, which allows us to ensure that these values are unique and we don't end up overwriting data if we say forget to change the sample name. We can specify the device integration time. So on this device, you can integrate 1 second or 2 seconds. And then there are several other columns if we want to look at those. And let's actually look at the first 15 columns. And so we also have the ability to see the sample ID, the latitude and longitude. So the data is also geotagged, as well as measurement description. And then we begin into our analytical data, starting at 1454 nanometers and going up to about 2400 nanometers. Oftentimes with this sort of data, we need to perform signal processing. And so in this case, I'm just going to use the standard normal variate and then plot just the analytical data. So I'm slicing my data just from when the first wavelength is, and then piping this function to at least help address some of the scattering. and then plotting that data here. And this already looks different from what the default rendering was in the web page. And so we visually can tell that we have a few patterns even within this data before we've applied any labels or done any clustering, where we have a set of samples that look like this. And I should have mentioned this earlier. When I went to the park, what I was doing was sampling various points of the soil. And so sometimes the grass is green, sometimes the grass is brown, other times there was a playground, or I was sampling pieces of plastic litter that was located on the ground. And we can see that most of the samples have this general pattern here where we have a lambda max around 1900 nanometers. Looks like we have another subset of samples that has a lambda max around 1700 nanometers, and a few other patterns that might exist in here. But we also see that we have some data that looks kind of wonky, like this orange trace here, where we have this flat region and some spikes that spike fairly low in the spectra. And thus we probably need ways to correct that. And over the course of the next few videos, we can walk through and correct those sorts of signals. So next, let's perform some clustering. And to do this, we're going to use PCA to decompose the data, simplify the data set. So right now we have a few hundred variables. Let's see if we can reduce those down to a few new variables called principal components. And we will do this on the SNVX data frame. So that was the data frame returned after we applied this transform there. And once we also use k-means with 4 clusters and change the cluster type to string, we get this new scatter plot here, where we can see that our data is breaking out into a dense group of orange points here, and we have these green points here. So these are, because they're closer, we know they're more similar to each other, but distinct based on the fact that we are using our 4 clusters. And then we have our blue and red, which are further from this initial 2. And so there's a lot we can do to dig in to understand, are these outliers? Are these part of some of the other structures within the data set that we know? Like I said, most of the data set should be soil, grass, sort of organic nature. And we have other components within our data, which we know are going to be plastic, either from the park structures, the swing, the slide, the rubber mat that's in the playground, or even the soccer goals that are in the field as well. And so some of the context we can get from this would be by understanding the patterns if we were to aggregate our data based on these clusters. But there's another way we can get some insight by plotting the geographic data. And so I mentioned earlier that the latitude and longitude of each measurement is recorded. And so not only do we have the chemical information, we have the geographic information, which is really powerful for understanding what's going on with the data. And the context that comes from geolocating each of those measurements is pretty profound. And so to do this, I'm using the Plotly Express mat box, and I have to use an access token that I've stored in the file accesskey.txt. I read that in, and then I perform this analysis here. And if we now look at the output, we can see that we have this Rio de Los Angeles State Park. This is where I was walking. And we have several samples that are overlapped on each other. So if we reduce our set, let's just focus on 0. This was the group here that was the most dense. It seems like we have the most amount of peaks within cluster 0. And on this figure, it is orange, but I'm using a different color scheme. And so on this figure, it is now red. And we can see that the red points are spaced across the entire park. So this is largely the cluster that's associated with the grass, whether it is maybe very moist soil or green grass, or if the soil was kind of dry. If we look at one of the other closely associated peaks, so we know that green was pretty close to this orange. Let's see what that looks like. So that's cluster 1. So one of the things that I know based on the geography of the data points is that this region here is near a cricket field. And so there is no grass, it's just dry dirt. So I'm guessing point 1 is where the ground was relatively dry. And based on what I recall about the park, this region was fairly dry as well. And the region around these tennis courts was also dry. So there is some context that I recall from the park that is pretty cool to see that overlaid with our measurements. Let's go to cluster 2. And cluster 2 looks like now we're getting into some of the plastics. And I say that because the points are fairly sparse. So this is probably a piece of litter that was sampled around the cricket field I mentioned before. And this region here, I know, is the actual playground with the plastic structures. This area here is the baseball field. And I actually was sampling along the plastic covered fencing. That's usually like yellow plastic so that the players don't run into the fence. And back here, again, this is probably litter. And if you look at cluster 3, it's primarily centered around this playground area as well. And we have this random piece here. So these are probably pieces associated with the playground, like the slide, the swing, even the rubber mat that's on the ground. And then this lonely peak here is likely due to litter. Now, interestingly, these 2 points here are on the opposite side of the soccer field. So I'm guessing these are the soccer goals. So we can already see some related peaks, even though they are dispersed geographically. Chemically, they're really similar. And now we have all this data to help us to tell a compelling story about what we know about the chemical composition of these relative clusters. So this is just an overview. Obviously, there's way more analysis we could do on even just this data set. And I will intend to do that and then walk through a more tutorial style. But I want to show you what was possible with this sort of device where we can now make chemical measurements in the field and provide context based on the geodata, the chemical data, the observational context that we can provide alongside this data set. If you enjoyed this video, like, comment, subscribe, especially you want to be notified when the next video comes out, and I'll see you in the next one.
Subscribe to the channel.
Peace.